And in my mind, I think these are kind of easy because it works out exactly how you think it would work out. Like here we've got the integral from 1 to 2 of the integral from 1 to x of 2xy plus 3y squared dy dx. So the first thing we're going to do is just solve the inside integral. And then we're going to solve the outside integral after that. But it's really not, really there's no part of this that's like really brand new or really difficult. So for the inside bit, we have to take the antiderivative with respect to y, because this is dy on the end. So the antiderivative with respect to y is going to be xy squared plus y cubed. And then we're going to plug in the values 1 and x for my y. Oops. So the first thing I'm going to write is x times x squared plus x cubed, and then minus x times 1 squared plus 1 cubed. So just plugging in the bounds of integration into just my y variable. And we'll simplify this a little bit. And x cubed plus x cubed is going to be 2x cubed. And I've got minus x minus 1. And then we take the antiderivative of each of these. So this is going to be 2 over 4, or 1 over 2, x to the 4th, minus 1/2 x squared minus x. And we're going to use the bounds 1 and 2. So I'll have 1/2 times 2 to the 4th minus 1/2 2 squared minus 2 minus 1/2 times 1 to the 4th is just 1/2. 1/2 times 1 squared is just 1/2, and then minus 1. So this is going to be 8 minus 2 minus 2 minus negative 1. So it's going to be 4 plus 1. So it should be 5.
So for the first integral, did you just treat x as like constant?
Exactly, yeah. Exactly. So whenever I took the first antiderivative, I only take the antiderivative with respect to y. So you're right, we pretend x is constant, and then obviously y goes to y squared over 2, and so that's why the 2 goes away. And then y squared goes to y cubed over 3, so that's why the 3 goes away. But yeah, we just pretend that x is constant in that case. Yeah, okay, so that was the right answer. Does that make sense though, how you do this? Yeah. So I don't think there's anything tricky, just being careful. Now, the area of this shaded region in the plane is obviously 15. You could just count the squares. But the way your textbook wants to teach this is by saying you could calculate this area in the plane by doing this. You could take the integral from 3 to 8 of the integral from 2 to 5 of 1 dy dx. And that should give you the area of that region. And so the idea here is, whenever I say the integral from 2 to 5 of 1 dy, it's saying I'm allowing my y values to go from 2 to 5. And then for the outside integral, where I'm going from 3 to 8 in my x variable, that's just allowing x to go to 3 to 8. So by defining these bounds of integration, I'm actually talking about or describing an area in the plane. And if you do this, hopefully we get the answer 15. So the antiderivative of 1 with respect to y should just be y, but we plug in 5 and 2, so it should be 5 minus 2, which is 3 dx. And so now if I take the antiderivative of 3 with respect to x, it should be 3x. So in other words, 3 times 8 is 24, minus 3 times 3, which is 9. So 24 minus 9 is 15. So that's a way that you can calculate areas in the plane, is if you use the bounds of your double integral to describe what x and y values are allowed. Does that make sense?
If you did three integrations, would that be like a rectangular prism?
Yeah, you could do volumes in three-dimensional space with 3 integrals. And we're going to do that in another section that's coming up in like section 14.6. We're eventually going to do triple integrals, yeah. Okay. So if you have this region, I know there's an easier way to do this. You could actually do this with just single integration if you take the integral of sine minus cosine, because on top of this shaded region, that's just the sine curve. I know because it passes through the origin. And this curve on the bottom of the shaded region is going to be my cosine curve since it passes through a y-intercept of 1. So the easy way to do this that we did at the very beginning of Calculus 2 would just be to take the integral from, let's see, this is pi. So that would be pi half. So the integral from pi fourths to 5 pi over 4. And then you would say, well, sine of x is my top curve, cosine of x is my bottom curve. And that's how we did it in Calculus 2. But, scratch that. And another way you could do this that would have the same effect is if you took a double integral where I'm going to allow my y values to be anywhere from cosine x to sine x. And then I'm going to allow my x values to be anywhere from pi fourths up to 5 pi over 4. And I'm just going to have 1 as my integrand. And you can probably tell that whenever I evaluate the inside integral now, integrating 1 with respect to y is just going to give me y. And then if I replace that y with a sine x minus a cosine x, then again, this is just going to give me the Calculus 2 version, which is the integral of sine x minus cosine x dx. But the point of this example and what I'm trying to illustrate is that you can use the bounds of your double integral to describe regions in the plane with different shapes. And we will eventually get to a point where we have an integrand that's more interesting than 1. And so we're going to be integrating multivariable functions over a region in the plane and not just an interval on the x-axis. And so It's cool, it's totally allowed if on my inside integral where I'm integrating with respect to y, I can have functions of x be my upper bound or lower bound or both. Because eventually I'm going to replace the y's with the functions of x in my integrand, and then at the end, whenever I integrate with respect to x, then it's going to go away anyways, and it's going to give me a constant value for my solution. So like in this case, the antiderivative of sine is going to be negative cosine. The antiderivative of negative cosine is going to be negative sine. And this is going to be from pi over 4 to, oops, sorry. Not the integral anymore, we're just evaluating this. At 5 pi over 4 and pi over 4. So let's see. Negative cosine of 5 pi over 4 oops. Well, cosine of 5 pi over 4 would be, let's see, it should be negative root 3 over 2, is that what you said? No, negative root 2 over 2.
Root 2 over 2, and then negative.
Yeah, negative root 2 over 2. So, negative root 2 over 2 for negative cosine of 5 pi over 4. And then minus sine of 5 pi over 4, which is also negative root 2 over 2, I think. And then minus negative cosine of pi over 4, which is root 2 over 2, minus sine of pi over 4, which is root 2 over 2. So this is positive root 2 over 2 plus positive root 2 over 2, which is root 2. And then minus, these are negative, so again I'm just adding. So this should just be 2 root 2, I think. Okay. Lots of minus signs there. So, new example. What if I want to find this area? So there's the easy calculus 1 way of finding this area. You say, okay, this curve is y equals square root of x. And so the straightforward calculus 1 way of doing things would say, let me just take the integral from 0 to 4 of square root x dx, and that would give you the right area. But I think the point of this chapter in the textbook is to describe these areas in the xy plane using double integrals, and so that's what we're going to do. I'm going to allow my y variable to be anywhere between 0 and square root of x. And then I'm going to allow my x's to be anywhere between 0 and 4. And so if my integrand is 1, then those bounds of that double integral are describing that region in the plane. And if you were to work this out, this should give you exactly the calculus 1 version of the integral after you evaluate the inside integral with respect to x. Then the outside integral is going to be just the calculus 1 version of the thing. But again, the point is that eventually we're going to have an integrand that's a multivariable function, and when the integrand becomes more interesting, we might want to integrate the multivariable function over a region. And so this is how you would define the bounds of your double integral. So this example says, find the area of the region using both possible orders of integration. And by order of integration, I mean I've got a dy and a dx. And I could actually swap the order of integration if I want to. So like another way I could have written the same integral for the same area is this. I could have said that, let me write dx first. So So I'm first integrating with respect to dx and then dy. So now I've swapped my order of integration. I'm going to say, let me allow my y variable to be anywhere between 0 and 2. But if I allow my y variable to be anywhere between 0 and 2, that means my x variable has to be between y squared and 4. This is kind of important, but it's an important skill to be able to say, this curve is y equals x, square root of x. But if you think of x as your dependent variable, this curve also represents x equals y squared, right? It's like if you turn your head, then you can imagine the y squared parabola like that, and it's the same curve. And so that's why I'm telling you that these two double integrals are equivalent. In this one, I'm saying, okay, my x value can go between 0 and 4. My y value can be between 0 and the square root of x. But in this one, I'm saying, okay, let my y value be anywhere between 0 and 2. But then for my x value is going to be somewhere between y squared and 4. So it's a different perspective, but it's talking about exactly the same area. So just for fun, I'll go ahead and evaluate these. Like, let me do the blue version first. So this is going to be the integral from 0 to 4 of y evaluated at root x and 0 dx. This would be the integral from 0 to 4 of root x dx. And the square root of x is just the 1/2 power. So this is just power rule. And the x to the half is going to become x to the 3/2 times 1/2. We evaluate this at 4 and at 0. And so if this were 4, then the square root of 4 is 2, and then 2 cubed is 8, and then 1/2 of 8 is 4. And then if x is 0, then it's 0, so the answer is 4 for the area. Oh, you know what? I made a mistake. I was thinking about derivatives, but do you see my mistake here?
Yeah, I was like,
Okay. Well, I'm glad you got it. Yeah, so this shouldn't be 1.5. It should be what? 2/3. Exactly. Yeah. So, good catch. So now this would be 2/3 of 8, which would be 16/3. That would be the answer. Okay. Now what if I try to evaluate the other way of doing this, where I had dx and then dy as the opposite order of integration, where this was going to go from 0 to 2, and this was going from y squared up to 4. Then this would be the integral from 0 to 2 of x, because the antiderivative of 1 with respect to x is just x. I'm going to evaluate that at 4 and at y squared. So that's going to be the integral from 0 to 2 of 4 minus y squared. Oh, that should be dy. dy, which would be 4y minus y cubed over 3. Ooh, thank you. Evaluated at 2 and 0. So if y is 2, then that's going to be 8 minus 8 thirds. So it'd be 24 thirds minus 8 thirds, which is 16 thirds. And then if y was 0, then the whole thing would be 0. So again, I got the answer 16 thirds. I should have the same answer if I'm calculating the area of the same region. And again, this is just two different ways of doing a double integral where I've swapped the order of integration. I say that this is an important skill because I think here in a couple weeks we're going to have some integrals where one order of integration might be really, really difficult. And if you just swap the order of integration, the problem becomes a whole lot easier. And so if you have the ability to see this both ways and swap the order of integration and still adjust your balance if you're talking about the same region in the plane, then that might make your life easier and might shorten the calculations. Does this make sense, George? Okay. Okay, so let's do this example. I've got integral from -1 to 1 of integral from -2 to 2 of x squared minus y squared dy dx. Okay, so just thinking about the inside integral. What's the inside antiderivative of x squared minus y squared with respect to y? Yes. Yeah, so, George, in case you missed it, when you take the antiderivative for this inside integral, the one with respect to y, we pretend that the x is a constant, and then we only take antiderivatives of y. Yeah. Yeah, just like a partial derivative, but this is, I guess, kind of like a partial antiderivative in a way. Oops. So then we're going to evaluate that stuff in the middle, where y can be -2 and 2. So this will be the integral from -1 to 1 of x squared times 2 minus 1/3 2 cubed minus x squared times -2 minus 1/3 times -2 cubed dx. So I'm going to simplify and collect like terms. For my x squared terms, I've got 2x squared plus another 2x squared, so I could write 4x squared. And then for my constants, I've got minus 8 thirds, and then another minus 8 thirds. So that's going to be minus 16 thirds, I think, if I did my math right. Now we take the antiderivative with respect to x, which should be 4/3 x cubed minus 16/3 x, evaluated at 1 and -1. So that's going to be 4/3 minus 16/3 minus -4/3 minus -16/3. So that's going to be 8/3 minus -16/3. Hold on, so that's -32/3.
The first one being -12/3.
Oh, sorry, yeah. I was looking at just the 4/3 together, and then I was looking at just the 16/3 together.
Oh.
No, I wasn't doing the parentheses. If I were doing the parentheses, then you're right. 4 minus 16 would be -12/3. And then the next set of parentheses would be -4 plus 16, which would be +12/3, except I'm subtracting it, so it'd also be -12/3, like that. So yeah, -24/3. Did I do that right? Probably. And so what this means essentially is like, let's talk about the meaning of this. In my little xy plane, I'm allowing my x values to be anywhere between -1 and 1. And then I'm allowing my y values to be anywhere between -2 and +2. So there's a little region in my plane, a rectangular shaped region. And in that rectangular shaped region, I'm evaluating this function. I've got a multivariable function. It's a function of x and y. And it's x squared minus y squared. And what I'm saying is I'm integrating this function over this entire region. Which is kind of like sampling a whole bunch of points inside that region, taking their values of that function, and then just sort of adding them up for little tiny areas that are like dx times dy. You know, if dx is just a little increment of length in the horizontal direction, and then dy is a little increment of length in the vertical direction, then dx times dy gives you a little increment of area, a tiny little square of area, right? And so these kind of double integrals are saying, hey, let me add up the values of my function of two variables in this region of my domain. And we're gonna talk a lot more about that as we go on, but that's kind of the idea behind doing double integrals. So it really only applies to, it's really only interesting for multivariable functions. Okay, so here, this time again, we've got a function of two variables as my integrand, and I'm going to integrate this function over this region in the xy plane. And here's my function of x and y. But this region in the plane that's described by those bounds of my integral is going to be the region where x can be any values from 0 to infinity, and the region where y can be any value from 0 to infinity. So the region I'm integrating over now is the entire first quadrant. I'm saying, hey, take this 2-variable function and integrate that 2-variable function over the entire first quadrant. But we're going to solve this one integral at a time, and we're going to solve it the same way we did improper integrals in Calculus 2. So this will be the integral from 0 to plus infinity of, and then I've got to take the antiderivative of that integrand with respect to x. And I can do that antiderivative with respect to x if I use a u substitution, where I could say that u is equal to negative x squared minus y squared. So that way du, and again, this is with respect to x, right? So du is going to be negative 2x. And that means hold on, let me think about this very carefully. Yeah, okay, I think what I'm doing is fine. So that means dx is going to be like negative 1 over 2x du. So after I make that substitution, let's think about how it would look. I'm going to have negative 1 over 2x times x times y times e to the u du. So the 1 over 2x, and so we can get rid of that x, right? Those cancel. Don't forget about those. And I don't have to worry about the y whenever I take the antiderivative with respect to u. But let's change my bounds of integration. By plugging in, let's start with the 0. If I plug in 0 for x, then u is going to be equal to negative 0 squared minus y squared. And so that means my lower bound of integration after I make the substitution should be minus y squared. And then if I plug in plus infinity for x, and u would be negative infinity squared, or just negative infinity minus y squared. So maybe that should be my upper bound, is negative infinity minus y squared. See how that goes. Since the negative 1/2 is just a constant, I can put that outside the integral, just like we've always done. And since when I'm taking the antiderivative with respect to u, I consider y to be a constant. I just can write the y right there. And now I've got to think about the antiderivative of e to the u, which is just e to the u. And then I want to evaluate e to the u at negative infinity minus y squared and minus y squared. Now the thing is, regardless of the value of y, whether y is 0 or any finite number up to positive infinity, this upper bound is going to essentially be negative infinity as I start to allow u to approach negative infinity. And so the limit of this function e to the u as u approaches negative infinity is 0. Yeah. If you remember the exponential function, then the limit as u approaches negative infinity of e to the u is 0. So that means the upper bound here, whenever I'm like evaluating this thing, the upper bound here is 0. And then the lower bound is what I get whenever I plug in u equals negative y squared. And so this will be 0 minus e to the power negative y squared dy. So my new integrand is going to be, I'll make that a plus to get rid of my minus signs. It's going to be y e to the power negative y squared dy. Yeah, and so I could do another u sub. So if I set w equals negative y squared, then the derivative of w with respect to y would be negative 2y. So that would mean dy is equal to negative 1/2, or sorry, negative 1 over 2y dw. So the y's are going to cancel, and I'll have this negative 1/2 e to the power w dw. So that's negative 1/4. Oh, my new bounds of integration. So if I plug in y equals 0, then w equals negative 0 squared, so my lower bound is still 0. If I plug in plus infinity, w is equal to negative positive infinity squared, so that's going to be negative infinity for my upper bound. Now I have to take the antiderivative of e to the w, which is just e to the w, and evaluate that at negative infinity and at 0. The limit of e to the w as w approaches negative infinity is 0. We talked about that just a second ago. So this is going to be negative 1/4 times 0 minus e to the power 0. E to the power 0 is 1, so that's negative 1, and this answer is 1/4. If you've got a double integral, right, and normally we've got like a function of two variables, x and y, and then you integrate with respect to x, and then you integrate with respect to y. And you have to do it in order like that. And that's generally how things go. But this is important. This doesn't always work, but only if this function of two variables can be rewritten as a function of x times a function of y. Sorry, I shouldn't use the same letter. But if you can rewrite your function as some function of x times some function of y, then you can do this. The double integral of your function of x times your function of y with respect to x and y is equal to, I've run out of room. Let me write it up here. It's equal to the integral of the y part. Sorry, that should be an h. The y part with respect to y times the integral of the x part with respect to x. Okay. So let me point out the two cases where this works and doesn't work. In this integral, my function of x and y was x squared minus y squared. I cannot write this as a function of x times a function of y, right? There's no way to do it. So you can't use that trick on this double integral. But in the one we just did, my function here of x and y is x times y times e to the negative x squared minus y squared. I could rewrite that as x times e to the negative x squared times y times e to the negative y squared. So here is a function of only x, and here is a function of only y, right? So I've got my integrand is just a function of just x times a function of just y. And since that's true, a shortcut for this problem could have been this. I could have said this double integral is equal to the single integral of x e to the negative x squared dx times the integral from 0 to infinity of y e to the negative y squared dy. And this would have saved us a lot of time, especially because in this case, those two improper integrals have the same value, right? The only difference between them is the symbol we used. In this first integral, the symbol is x, and in the second integral, the symbol we use is y. But which symbol you use, that doesn't affect the value of a definite integral. And so the first integral has value 1/2. The second integral, you would find has value 1/2. And then when you multiply them together, then the value of the double integral would be 1/4. So it's a really quick, easy trick for simplifying some double integrals. But do you guys see how it works? It works for this one because it's a function of only x times a function of only y. But it would not work for this one because I can't make that a function of x times a function of y.
Will that work too if you have like a function of x, y, and z?
Yeah. So if you had a triple integral, but the integrand is a function of x times a function of y times a function of z, you could make it a product of 3 single integrals like that.